Murilo, tudo certo, pode começar, tá bom?
Ok, obrigado, Larissa. Bom, então, boa tarde a todos. Carsten, Rogério, Thales. Então, vamos começar aqui a defesa de projeto de tese do Thales. Eu vou passar a palavra, então, para o Thales, que pode começar a defesa.
Okay, so as a part of the qualification for the PhD at CDPF, I will present the research of magnetic monopoles using what we call the missing transversal energy approach and the luminosity monitoring with the Z counting method in the CMS experiment. And this work was developed in the supervision of Carsten Hensel. So just a quick outline on the presentation. Some words about the LHC, the CMS experiment, with the focus on the luminosity, the muon system, the trigger system of the CMS, and a particular feature of that trigger system. For the Z counting about the motivation, the method itself, and some of the results that we derived for 2023. And in the search of magnetic monopoles, the theoretical motivation, the methodology, the analysis strategy employed, and probably the best part of the contribution, the materials approach, and some of the results that we already developed. So, starting with the LHC, you know that LHC is 27 kilometers circumference particle oscillator, which is mainly composed by its for the biggest principal detectors, CMS and Atlas, in the scope of multi-purpose experiments, and ALICE and LHCb, which is respective purposes and objectives. So the LHC was developed to provide a higher center of mass energy environment to allow the study of standard model processes and, if possible, as a tool to derive some limits and exclusion zones for the sum of the beyond the standard model process that we are studying. So inside the LHC, we have the CMS, the compact muon solenoid, which is a multi-purpose experiment. It was designed to provide a measurement and a capacity of distinguishment between all the particles that originated from a proton-proton collision under the high luminosity environment conditions that the LHC could offer for its experiments. So it was built when what we call the cylindrical shape concept to enclose the interaction points with barrel layers around the beam pipe, and in order to provide the hermetic closure of this barrel, and also add the forward coverage for the detector for some of the studies, two end cap discs were placed on the top of each side of the barrel. So since the CMS is it's divided in different subdetectors, each one of these detectors provides information which are complementary to each other and are combined to, let's say, perform a given analysis, for instance. So I think we have been just a quick focus on the muon system, since we know that the muons are characterized as minimally ionizing particles, and for that reason, it has the dedicated detector for such particles, which is the muon system or the muon chamber, which is located in the outermost part of the CMS, providing muon detection for the range of solar rapidity smaller than 2.4. So on the context of LHC and CMS, we can have some words about the luminosity and more precisely the instantaneous luminosity, which can be defined as the intrinsic characteristic of a given particle collider, and could be understood as well as the capability of such particle collider to produce a certain number of interactions, even for the different probability occurrences for such interactions. And the instantaneous luminosity, the knowledge of this quantity, the measurement, and the uncertainties plays a crucial role for the LHC precise measurements, where we can achieve a high statistical significance for such results if we have higher luminosity or a luminosity with more precise measurement. And when we talk about the instantaneous luminosity over, for instance, the course of a year or a month, we have to define what we call the integrated luminosity, which is basically the aggregation of these the instantaneous over a certain period of time. You can see on the right side, in red for 2022, the integrated luminosity for 2022, and in purple, the integrated luminosity delivered for the CMS in 2023. And this integration comes from the, let's say, this integration of the instantaneous luminosity, which is a function of the number of bunches that are available, the number of components of that bunches, and the effective area of collision, for instance. But that is let's say, several ways to measure that luminosity, but one which is quite interesting is to perform this measurement with physical processes, which is very interesting in the point that we can exploit processes that have a very clean signature. And in this approach, the largest uncertainty will come from the knowledge of the center of mass energy. In the case of the CMS, so on, it's a constant value throughout the whole run tree, for instance. And with this, the application of this approach in previous experiments, such as LAP and VALU2, they achieved a very interesting result on the uncertainty of the luminosity measurement. So this approach of the physical process and its further improvements are, let's say, propagated throughout the experiments, reaching where we have now is the Z-boson counting method in the CMS. So why this method is interesting is because it's suitable for the LHC data take conditions that we have. Things we can exploit the behavior of a constant center of mass energy and current, and for consequence, cross section of some process throughout the whole run, for instance, for the run tree. And with these characteristics, we can achieve using this accounting method a long-term stability and linearity of the results. So it is very promising in the sense that when we take the reference luminosity, for instance, which is our target, for each year they have a different calibration, which can lead to uncorrelated uncertainties. They're not the case for the Z-counting method. And how can we determine this luminosity? And with the method, we can extract the number of Z-bosons, or let's say the efficiency corrected Z-bosons, which is corrected by the efficiency of the detection and the acceptance of the detector and so on, and the fiducial cross-section of the given process. And why we choose the Z in a pair of muons, since it's a process that has a large cross-section and could be characterized with a clean experimental signature, with a flatter background spectrum, and a peak around the boson of ZMS. So it's probably one of the most promising channels of choice to perform this study. And with the number of Z-bosons in hand and the cross-section of such process, we are able to provide estimative a number for this luminosity and provide a further comparison with the reference one in the previous step. But since this is a method that is developed in parallel with the Atlas, have to define some fiducial phase space to have our measurements. And for this definition, we have the production of muons using the Ariane mechanism without intermediated dibosonic contributions, city bar, and so on. And our muons should be within the acceptance of the detector, 2.4 value, smaller than 2.4 in total rapidity, and transverse momentum higher than 27 GV. And we further restricted the invariant mass of the muons pair should be within the range of the Z peak, which can be defined between 66 and 116 GV. So how can we do the method? How can we apply the method? We perform a fit on the invariant mass distributions of the pair of muons in two different scenarios. The first one for the scenario that just one of the muons fires the LHT trigger, and the second one when the two muons fires the trigger. So we can perform this fit, let's say this part of fits, for each 20 inverse picobars of data. And with this application, we are able to extract in a simultaneous way both the single muon trigger efficiency to further correct the number of Z-bosons, and the most important quantity, the efficiency corrected number of Z-bosons. So if this number in hand and the cross-section that we know from the Z-boson in 2 muons, we can further derive what we call the Z rate, the Z boson rate. And in these three different plots that we have three different fields from LHC. We can, let's say, define a field just as a set of runs, different runs of the LHC for the given period of the data taking, for instance. And we separated three fields with higher the instantaneous luminosity to better, let's say, explore the method and the results. So the three fields have more or less 700 or 800 inverse picobars of instantaneous integrated luminosity. So these three fields are from 2023, but we have similar results for 2022 as well. And you can see in these plots two different quantities. In black, the Z boson rate, or the instantaneous luminosity calculated by the Z boson counting method. And in red, the reference luminosity. And you can see that for the three fields, even for the points that are, let's say, appears to be out of the general behavior of the distribution, we have a very good agreement between the two independent quantities. So since these fields are let's say, both years of the data take are composed by a different number of fields, we have similar results for 22, 23, and the numbers, let's say, start with it's 016 all the way to 9045. So it's a quite large number of fields. And since looking just field by field is quite exhaustive, you have to let's say combine these fields in a way to provide a more general result to achieve these results that we call the absolute luminosity from the Z boson rates. And in the histogram on the right, we have a ratio between the Z rate or the Z boson luminosity by the reference luminosity. And you can see, judging by the average value of that rate, that you have a very good agreement between the two quantities, because the average is more or less in one, with a narrow distribution. And with these, you can see that we have a very adherence for the combination of all the 2023 fields. But if you are interested in to know how this ratio between the luminosity from the method and the reference one behaves throughout the different fields of the year, for instance, 2023, you can look on the plot on the bottom side, where you can see the different measurements for this ratio for different fields that we have in the green points, and the average value of those measurements in blue, and you can see that you have a very stable behavior throughout the year. The value is around 1, and we can further develop the similar plots for both 2022 and 2022 plus 2023. So it's a possibility as well. And the scatter plot could also be deriving the function of the integrated luminosity instead of the field number. But the field number, I think it provides a more explanatory view of the method. So this was for the Z counting part, the luminosity monitoring part, and for the second part, the monopoles search. First, let's say the theoretical motivation behind it. It was firstly proposed to make the Maxwell equation symmetric in order to complete the electromagnetic duality. But Dirac provides a very different idea of the magnetic monopoles. Since it was proposed that when we have the quantization of the angular momentum, we naturally provide the quantization for the electric charge as well, if that is a monopole, or let's say a solution in the type of monopole. And Dirac derived what we call the Dirac quantization. It relates the charges of the particles with an integer. But from, let's say, independent studies, it was shown that for the environment of spontaneous broken gauge symmetries, the context of the electromagnetic group, especially when this group is the symmetry is broken by the Higgs mechanism, that we have now, we should define a model similar to the electric model from the Weinberg-Laschel and so on, and choose a proper electromagnetic field tensor to satisfy some conditions, for instance, high Higgs field along the v direction, which we reach a point that this tensor satisfy the maxwell equations except for the one term. And this one term, this equation are not satisfied, we have our possible magnetic monopole solution. So when we further develop the calculations, we indeed see that this solution is a solution that satisfies the Dirac quantization and can be defined as a magnetic monopole type of solution. And for that case specific, we can say that is a monopole with two Dirac charges. But okay, how can we treat this particle? How can we study this particle in the context of the colliders? And that's let's see, and its further friends. So we reach this side and see that define that the charge carried by a monopole it's a multiple of the fundamental magnetic charge provided by Dirac. And we find that a magnetic monopole is equivalent to an electric charge particle with, let's say, almost 70 times the elementary charge of electron, for instance. And with for these interesting, let's say, this peculiar behavior, have a particle that have a high ionization capacity in the order of 5,000 times the capacity of a minimum ionizing particle. So these characteristics should be further exploited in order to study these particles in the colliders context. But since for these, let's say in the theoretical part of the process, since we have a high value of the Dirac charge and high complete constant between the photon and the monopole, we cannot deploy perturbative methods to calculation the production process, the cross section, and so on. We can just provide some limits for these, and for these, providing this development of limits should study these particles in the LHC context. Since they are accessible to the LHC context, since they are proposed to be in the order of few TeVs of mass, with the exclusion of masses below 1 TeV by some results of the atlas, and respectively be pair produced in the detector and manifest themselves as these highly ionizing particles, these high peculiar type of particles. So how can we identify these particles within our detector? Since the most interesting character feature of this particle is ionization capacity, we should look from the tracking part, the tracking reconstruction. So starting with this, since the monopoles are magnetically charged, we would gain energy, we interact with the magnetic field of the CMS, which result in a curvature along the beam axis, which doesn't happen for the, let's say, ordinary particle. But this peculiar behavior will lead to a highly inefficient CMS reconstruction algorithm, the standard reconstruction algorithm of the CMS. So this motivates a development application of a improved version of this standard reconstruction algorithm. And in this, let's say, improved version, the idea is to combine different track segments reconstructed by this standard algorithm to compose a curvature track to be associated with this monopole candidate. So this combination is achieved by two fits, one circular and one parabolic fit. And from these fits, we can extract, as we call, quality cuts, some parameters of the fits, and they are implemented in order to as selection cuts for our analysis. For the further identification of the analysis, we can establish the track sets for our monopole. Now we are able to measure the ionization of such track set. And on the right side, you can see in black the fraction of saturated strips for the, let's say, ordinary particle, the background, for instance. And within the red dots, you can see the fraction of strips that are saturated by the monopole with mass in the order of 1 TeV, and you can see there is a clear and significant difference between the two quantities, and we should explore this difference with some approach, which is in this case a definition of a variable which take into account the probability of the strip saturation, which is different for the two set of particles, and within this variable can combine the total number of strips that we have available with the total number of the ones that are saturated by the passage of the monopole. So it is a definition where you can see the idea of significance, with the binomial function and the number of total strips, iterated strips, and a factor of, let's say, the probability of minimum ionizing background to saturate the strips. We can derive this particle, this variable, to be further used. And a second interesting feature of a magnetic monopole type of particle, since it carries a huge amount of charge and have a significant high mass, it will deposit all of its energy in a small, let's say, part of the detector, even just one of the crystals that we have in our electromagnetic calorimeter. So for this behavior, they define another variable, which is a ratio between the quantity of energy contained in the rectangles, 5 by 1 cells in the eta phi plane, divided by the number of the energy contained in the square of 5 by 5 cells, the same plane. So we expect for the monopole-like showers that this ratio should be around 1, since all of the monopole energy should be enclosed in just one single crystal, or you can say no more than that. No, in the strip, in the rectangle, in the small area of the detector, and for the ordinary electromagnetic shower, we could expect lower values for this ratio, and we can use this behavior, this difference, to further identify our monopoles. But we reach, let's say, the biggest drawback of the analysis, the biggest limitation of the analysis, which is the trigger system. This trigger system of the CMS is deploying at 2 different levels. The level 1 trigger, the L1, is deploying the hardware and using just the data from the calorimeters and the MIL systems, provide the hypothesis for the most varied type of particles. And for the high level trigger, we have a more robust decision and structured, which was deploying the software and uses information for the trap reconstruction, which is quite important for this analysis. And uses some information from the reconstruction algorithm. And part of this trigger system is what we call the strip fine-grained vector bitter, just as FGVB, which is built inside the L1 trigger and provide a rejection. The rejection, they use discard events that they understood to be what we call spike-like signatures. And these spikes, so spike-like, would be understood as anomalous energy deposits in just one single crystal. So we have a huge amount of energy in just one single crystal of the equal, which is exactly the kind of signature that we're expecting the monopoles to have in the interaction with the equal. But this behavior is quite inconsistent when we take in comparison ordinary electromagnetic showers. So for this reason, this feature of the triggered system should reject this kind of events, which is for some let's say some analysis just a spike, just a noise, and for our analysis it's our signal signature. So this trigger, this, let's say, spike killer trigger that they call, is the biggest drawback of the analysis. But how can we deal with this limitation? How can we, let's say, overcome this kind of limitation of the analysis? We can use the missing transverse momentum or missing transverse energy of the event. So how can we do this? On the right side, we have just a scheme for, let's say, a pair of monopoles in the detector. On the right side, we have the track, which is properly reconstructed in the equal, and you can see the cluster. But on the left side, we have a lost monopole, a monopole that is not reconstructed in the equal. And if we are, let's say, losing, you have not reconstructing a particle that is part of the process, part of the collision, for instance. We should read this absence of particle as a contribution of missing energy. So we can take advantage of this, let's say, pattern of the process to further exploit the uses of triggers that takes into account the missing ET contribution of the events. So if let's say, to make a resume, if you are assuming that one of the monopoles is killed by the trigger system, we should expect a signature of missing ET in that event. So we should look no further than this net signature, since, for instance, we do not expect to have associated undetected particles in this kind of process, such as neutrinos, for instance. So it's quite a promising way to overcome this limitation of the analysis. But if we try to apply a different set of triggers, in the match triggers in this case, we should have a different type of analysis with a different associated circuit. So this is the biggest part of the work, provides analysis in this different approach. So just for this work, that is the data sets that was used, the magnet let's say the pair of magnetic monopoles produced by the Gaussian mechanism with 1/2 spin and charge of just one, let's say direct charge or magnetic charge. But for the mass points, starting with 1 all the way to 4.5 TeVs of mass. And for this work, I just used the 2018 data sets, but we have available the data sets for 2016 and 17, concerning the run-through data table. So since the biggest limitation of the analysis is the number of events that we have available to work with, we should motivate to try to evaluate how to try to understand if you apply a set of requirements, for instance, a trigger, what will be the number of events that will survive this application. So we define our signal efficiency. And things very interesting in understood how the different trigger paths could behave, especially the one that considers math, lithium HE, behaves in this quantity, should calculate the signal efficiency for each one of these triggers. So we have let's say the standard one, the Photon 200, which is a single photon trigger, in the assumption that one monopole is lost. And we have two math triggers. The first one using the PF math, using information for the particle flow algorithm, considering that we have a particle flow object, for instance. And the second one using information that are contained in the Calo tower as part of the detector. So the questions that arise with this approach is, we will have higher number of events to do the analysis. And if it is the case, what will be the quality of these events? They will be the events that we are indeed looking for, or they will be, let's say, events with lower quality. So to answer this question, we have to have a look on the discrete variables and the ones that we defined previously, and on the left, the F51 in the equal part, and on the right, the idea significance, which relates to the tracking part and the saturation of the strips on the tracking system. So we can see for the F51 a higher number of events around 1, which is we're expecting, since is the signature of a signal. And you can say that to have a perfect region for the F51 higher than 0.8, for instance. And on the right side, the IDX, it deals with the combination of the total strips and the saturated ones. You can see that have two very different regions. The first part in the close to 0, which is minimum ionizing particles with not such ionization capacity. On the right side, the particles that we are most interested with, it's a high ionization capacity. So two things that we can extract this, have the preferred region that we can define for study these monopole particles. And when you look on the distributions itself, we can see that the particle flow metric and the metrics provide us a higher number of events, or you can say 27K, 13K, in comparison to just 8,000 events for the single photon trigger. So we have indeed a higher number of events available to perform the analysis, but I have two questions to answer. What are the quality of these events, and if this behavior will happen for all the mass points. About the quality of events, you can just have a quick look on let's say, the values of such measurements or such distributions. And they are quite similar. For the F51, for the IDX, there are the significant difference. We have 2.5 in comparison to 3.2, so it's let's say, significant difference between the two set of quantities. But for all the mass points, this behavior will be, let's say, carried through. We have, let's say, this factor of 3 available events, and you can see for this plot in the table, we have the number of events for this is our single photon trigger, and the number of events for the both math triggers that we are studying to apply. And in the let's say the right side of the table, the ratio between the one of the match triggers and the single photon trigger, and the second match trigger and the single photon trigger. And on the plot, you can see how this ratio is behaving for the different mass points. And you can see that, especially for the particle flow match trigger, this ratio is consistently above 3. And for the mass points in the middle, 2.5 all the way to 3.5, we can see that we have almost 5 times or even 6 times more events when we apply this particle flow match trigger in comparison with the application of the single photon trigger. So this is quite promising in the sense that it have indeed a higher amount of events to work with and to develop the analysis in the idea to overcome the limitation of events that we have previously. So just the conclusions. For the Z counting, we saw a good agreement between the quantities. We'll talk about that. But next steps, we continue to apply this method to 24 and 25 data taking period. And we plan to have some improvements of the application of prefiling, developing the Monte Carlo template, the derivation of mirror correlation factors, which is a topic that I do not dedicated much time in it in this presentation. But in the magnetic monopulse part, you can see that the application of the metric path indeed improves the signal efficiency, indeed improves the number of events that we have available, and this is consistent to the mass point that we have, especially for the ones between 2.5, 3.5 TV. And since the number of events, we can make the trigger choice of using the particle flow match trigger. And as the next steps, we should have a better understanding of the events that are triggered by the match triggers, how they could be compared with the ones triggered by the single photon trigger, which is the approach previously used. And since we have a different type of analysis, we should take into account the derivation of the systematic uncertainties that are related to the missing energy. So these are the next steps for the whole analysis.